Good morning, everyone, or good afternoon, depending on where you're calling in from. I'm Melanie Davidson. I'm the Director of Marketing at CISA, and I'll be moderating today's webinar, which is Future-Proofing Your Battery Energy Storage System, RFQ for Safety. So really, we're looking at how those out there that are looking to procure battery energy storage systems can do so safely, future-proof the system, and ensure that there is no loss of life or property when you are designing your system and preventing any issues that could occur. Next slide. So I'm Melanie Davidson. Again, I'm the Director of Marketing at CISA. Next slide. Today, the webinar is really going to be in 4 parts. So we're going to have 3 presentations, starting with Li-ion Tamer, who's going to talk to us about lithium-ion off-gassing. Next, we're going to have the Energy Safety Response Group talk to us about managing battery energy storage systems in a time of changing codes and standards. And then we're going to hear from Duke Energy, who is a leader in safety, and learn how they are applying best safety practices around their energy storage deployments. And then the last chunk of the webinar, we're going to really try to reserve at least 15 minutes to have a robust Q&A with these experts on that are joining us. Next slide. So a little bit of housekeeping. All participants are in listen-only mode. The webinar is being recorded. It will be available and posted to our website, as well as emailed out to all registrants. If you have a question, we definitely want to hear it, especially since we're trying to reserve time for Q&A. So you can type that into the questions box that's appearing on your screen. And if you have any comments at the end of the webinar, feel free to reach out, as CISA is here to serve you. Next slide. Okay, so a little bit about us. So the California Energy Storage Alliance, we're the definitive voice of energy storage in California. We're 100 members plus strong, and we're committed to advancing the role of energy storage in the electric power sector. We are a membership-based advocacy organization. We're technology and business model neutral, and we encourage people to come and learn more about our membership. Next slide. Our membership is really diverse, including associate members, which are load-serving entities and utilities, and then we have service providers, battery providers, developers. So we're a Big 10 organization. If you're looking to do work in California in the energy storage space, or if you're looking to learn about energy storage markets in a different state but want to see how a successful energy storage industry is being run, please consider joining CISA. We would love to add you. And in that vein, next slide, we now have a new offering for non-CISA and CISA members. It's called our Western Market Insight Service. And the idea is that energy storage is taking off across the West. It's really gone beyond just California now. And this is a monthly briefing from our energy storage experts that will let you know about procurement opportunities, RFP updates, everything you want to know about Western states that are participating in the energy imbalance market. It's a customized service. Subscribers will be able to help craft out the coverage. So we definitely encourage you to learn more by contacting my colleague Grace, whose information is at the bottom. Next slide. All right, so really quickly, we just want to know who is on the webinar today. So if you could just take this quick poll, are you a regulator, a policymaker, developer, utility, or a consultant? And really what we're trying to figure out is like, who's interested in learning about storage, about safety, who's owning safety in their organization, who's concerned about safety. So it's going to be helpful to our speakers to understand who's on the line today so that they can customize their comments to our audience. All right, Jake, I think we can probably close the poll and see who's online with us. Oh, great. Okay, so we have a bunch of developers, a lot of utilities, that's great, and consultants, wonderful. Well, we're very glad to have all of you here today. So let's kick off the presentation, starting with Li-ion Tamer. I'm joined by my friend from Ohio, Steve Cummings. Next slide, please. Steve is the director of the Sensors Business Unit at Nexteris, where he's worked for the last 16 years. He's worked in the area of battery safety for much of his career, including the design and development of safety-related products for the battery industry. And very cool, I just learned this, that he was the primary inventor of Nexterra's Li-ion Tamer technology. So super cool, Steve. He's an active subject matter expert for the development of codes and standards addressing gas detection and battery safety, and he's active with EPRI and CISA. So Steve, thank you so much for helping produce this webinar with us and for your willingness to support the industry as we always improve in our safety record. So please take it away.
Great, thanks Melanie, I appreciate it. And we're excited to talk on a couple different angles today. And what I'm going to be talking about is kind of the gas detection side of energy storage safety. So if we can go on to the next slide. We'll start with a basic question of what is Li-ion Tamer. And Li-ion Tamer at its core is a safety product that's designed specifically for lithium-ion batteries. And the way that it does this is by detecting off-gas events that are emitted prior to thermal runaway, and thus providing the opportunity to have the earliest warning of any detection system to provide indication that something's beginning to go wrong in the battery system. And because these events occur outside of thermal runaway, this can actually be used as an effective barrier to avoid catastrophic events. And these catastrophic events have occurred globally from North America to Europe to Asia and across industries from utility, commercial, and industrial, electric vehicles, and electrified ships. And these events are not limited also to historic events, but they really have continued to occur. In 2008, we began to hear about some of the energy storage system fires that were occurring in South Korea. They're now up to their 31st fire. The last one was documented 5 days ago in Yeongcheon, South Korea, at an 8.4 megawatt hour solar site. And on that same day, there was a battery fire on board the MF Brim Explorer, which is a hybrid ferry that was operating in the fjords of Norway, which was the second such incident in about a year's time. And there's also been a growing concern about the gas generation that's associated with these events. We're all now aware of the reports that were published after the APS fire in Surprise, Arizona, which was followed by another similar event in Liverpool, which is still being investigated. And there was also a lesser publicized fire and explosion at Griffith University in Brisbane, Australia in March of 2020, which was started in a lithium iron phosphate battery, which is a more stable battery chemistry. So, but the positive side of this message is that we can manage these hazards that are associated with these systems by taking a collective effort within industry to commit to safety and collaboration. So we appreciate the leadership of industry leaders such as CISA, who's supporting this discussion on battery safety, and as well as others around the industry such as EPRI, who's really doing a lot of work to try to bridge the gap between codes and standards, which are developed on a 3-year cycle, and how do we kind of develop industry best practices and get feedback to the industry on a more frequent basis. And they're doing a lot of that through some of their products like their pro forma hazard mitigation analysis that we're going to talk about a little bit later on in the call. And then also utilities whose leadership is developing a standard of care and setting industry best practices by taking an active role in safety. And so we're going to hear from Duke later on this afternoon. So we can go over to the next slide. We're going to ask another kind of high level question, and that is, what is off-gas? Off-gas, the event of off-gas is now defined in NFPA 855. And it's defined as the event in which the cell case vents due to an internal rise in pressure of the cell. And where that definition comes from is the UL 9540A cell level test. And during that test, there are 2 different events that are documented. So a cell is abused through thermal runaway, and the first event that is documented is in 7318, which is the temperature at which the cell case vents. And we refer to this as the off-gas event. And then in the next section, the temperature at the onset of thermal runaway is documented separately, which is the thermal runaway event. And there's the definitions. And if you can go one more slide. So what this does is this puts off-gas as a unique event within the stages of a battery failure, and thus can create an effective barrier to helping to prevent thermal runaway. So if you can go over to the next slide, we'll take a look at, again, another kind of high level question of what are the stages of a battery failure. And at Nexterra, we have a long history of failing battery cells. We've failed cells from many different manufacturers, chemistries, capacities, and form factors. And what we've done is we've taken that learnings and put them into 4 stages that we see as being common to all of these battery failures. The first stage that we identify is the battery abuse. This is going to be something that eventually will lead the cell into thermal runaway. It can be thermal, electrical, mechanical abuse. And what begins to happen is you get some cell damage. You get mechanisms that begin to operate inside the cell that will lead to an increased pressure in the cell that eventually will lead to stage 2, which is that off-gas event. If that abuse factor continues to happen, those mechanisms become increasingly exothermic, which leads to more heat release, which leads into thermal runaway, and you get smoke and fire generation, which often happen almost simultaneously. Once a single cell is into thermal runaway, then you begin to worry about closing that loop through propagation as it becomes a thermal abuse for adjacent cells. You go to the next slide. If we look at this within 2 regions, we kind of see 2 regions that become important, and we'll talk about these a little bit more as we go on. First is the preventative region that happens before the cell's in thermal runaway. And then once that cell's in thermal runaway, we're really into a containment region where we now have to deal with the effects and the consequences of that cell being in thermal runaway. So if you can go on to the next slide. One of the trends that we've really identified or seen within industry is that the industry has become increasingly focused on gas generation. And I have borrowed this slide from an EPRI presentation that Mike Simpson and Dirk Long put together. And I believe there's supposed to be a link at the bottom of it. If you're interested in seeing the entire presentation, if the link doesn't end up showing up, you can let me know and I'll be more than happy to send it to you. There's a lot of good information in this. But what I'm going to focus on is the trend that they identify here within these blue boxes. And we really began kind of as an industry with cell level failures, concerns over some of the well-documented incidents with cell phones and laptops, things that led to kind of a general understanding of the propensity of thermal runaway in lithium-ion batteries. And then in the 2010s, as we began to put more and more of these batteries into systems, increasing the energy density of the systems, in efforts to try and decrease the dollars per kilowatt hour of these systems, we began to worry about these propagation hazards. What happens when we get multiple cells that go into thermal runaway? This led to some standardized testing like that in UL 9540A to try to begin to address and understand what the hazards associated with the propagations would be. And then as we began to see some of these industry events unfold, notably the APS fire and explosion, the Liverpool and the Brisbane explosions that I referenced earlier, we really began to shift that understanding to there's a large need to understand the gas generation capacity of these failures and the consequences that are associated with them. So go to the next slide and we begin to ask the question of what do we do with this information? How do we begin to use this to develop industry best practices? And after the APS fire, there were 3 major reports that were released. One of them was from the UL Firefighter Safety Research Institute. And what they did is they really took the position of identifying what the contributing factors were that led to the incident, and then developing recommendations so that we can begin to take those learnings and put them into best demonstrated practices and kind of a standard of care of how do we better improve the safety of these systems to prevent these events from occurring again. The first recommendation that they came out with, I think, is very universally accepted, and that was around the training of firefighters and the emergency response training. And I think Tom and Nick will get into that a little bit more. But their second recommendation was really around gas detection. And that was that energy storage systems should incorporate gas monitoring that can be accessed remotely. They point out in the report that NFPA 855 provides only the minimum requirements for an energy storage system, and that even if the energy storage system at the APS site was installed today, it would not be required by code to have gas detection installed in it. And in spite of that, their recommendation is that energy storage systems should use gas detection. They follow up that section very quickly with recommendation 2.2, where they identify a variety of complicating factors that make gas detection difficult within energy storage systems. And in fact, they identify 9 complicating factors that we at Nexceris and in the development of the Li-ion Tamer system have really done a lot to address those 9 factors. We weren't surprised by the fact that they were identified as complicating factors. And unfortunately, we won't have the time to go into all of those today, as much as I would love to be able to dig into them. We don't have the time for it. But Li-ion Tamer is a gas detection system that is developed specifically for lithium-ion batteries and has already worked to address many of those concerns that were brought up in the report. So if you go on to the next slide, we'll get a little bit into kind of the nuts and bolts. How do we actually use gas detection as a barrier in energy storage systems? And we'll begin with the hazard mitigation analysis. And first and foremost, in NFPA 855, there is a requirement for energy storage systems to be presented with a hazard mitigation analysis. And there is a reference hazard mitigation analysis that's been made available in some of EPRI's products that they release. Again, it looks like it's kind of cut off, at least on my screen, but there's a link to it there at the bottom. You can get the slides afterwards and follow it and find out more. But they have decided to take an approach that uses a bow tie analysis, which is a specific type of hazard analysis that's kind of depicted there in the graphic on the right-hand side. And the bow tie is really centered upon that top level event. So you identify a hazard and you look at the various threats that can lead into that hazard. And then coming out of that hazard, you're looking at the consequences or potential consequences if that hazard were to occur. So this causes this, resulting in this. And one of the things you'll notice, similar to the stages of the battery failures that we talked about in an earlier slide, this is also broken into preventative and mitigating regions. And the idea here is that you want to identify as many barriers to the threats that lead into that top level hazard, and then also barriers on the other side that can help minimize the effects of the consequences if that top level hazard were to occur. So one of the things that's pointed out in the document is that there are gas risks that are identified as both threats and consequence pathways. And so therefore designing a system with barriers that has gas detection in mind that protect both the threats as well as the consequences it's vital to a holistic approach to using gas detection in energy storage systems. So you can go on to the next slide. So we'll look a little bit more specifically as using gas detection as barriers. And what we've done here on the bottom, this little table is kind of comparing two different types of gas detection. There's conventional gas detection, which I would define as your hydrogen, your CO detectors. And then we're comparing that against off-gas detection, which would be the Li-ion Tamer system. So you see on conventional gas detection systems, you can use the conventional gas detection as a barrier to the consequences of failure. So this would be after a cell is in thermal runaway. What happens is as that heat inside the cell begins to increase, the gas release rates increase, as well as the composition of that gas will continue to evolve. And you'll get much more hydrogen, you'll get more CO that come out during thermal runaway. So traditional gas detection or conventional gas detection can be used as a barrier to help measure and understand, give you situational awareness of what's going on inside the energy storage system only after a failure has occurred. However, conventional gas detection systems are not designed to work in the preventative region, as they're not designed to detect that off-gas event. But when we compare this with off-gas detection and Li-ion Tamer, we look at protection in both the preventative as well as the mitigating regions of the HMA. And we'll start on the preventative side. There was a 2-year study that DNVGL conducted on marine battery safety. And one of the key findings with respect to gas detection that they had was that the gas detection system, Li-ion Tamer, that was used, is that early gas detection coupled with correct shutdown measures is an important safety barrier for an energy storage system. And so we're looking at that section on the left-hand side under the preventative side and how we can use off-gas detection systems as a barrier to the threats that can lead to those top-level events. But at the same time, if we look at the other side of the equation, Li-ion Tamer can also be used to continue to monitor a cell if it were to go into thermal runaway. So if we look at an event like a irreparable mechanical damage to a cell, and there's nothing that you can do to prevent that cell from going into thermal runaway, and you enter into that condition, the Li-ion Tamer system is still capable of telling you where that gas has spread to, where the gas is recovering back to the pre-incident levels, and can kind of follow that failure all the way through. And we'll show a little bit of data here that kind of highlights that. So if you go over into the next slide, and this is actually our last slide, but I couldn't help but provide a little bit of data in here and talk about this. This slide shows two different tests that we ran. The first test is really designed to show the early warning capability of the Li-ion Tamer system. So what we did is we took a lithium-ion battery cell, we thermally abused it into thermal runaway, and you can see that large spike on the right-hand side of the graph showing that it has entered into thermal runaway. And what you see there in the blue line is the off-gas monitoring signal provided by Li-ion Tamer. And in this case, there's about 5 minutes of early warning before thermal runaway that the off-gas detection system can provide. The second test that we ran is designed to show how this can also be used as a barrier to thermal runaway. And in this case, we heated the cell in the same manner, only this time when the off-gas detection indicated that the cell had vented, we turned off the abuse and allowed the cell to cool back down, back to room temperature, which indicates that the cell is not in thermal runaway at the time of the off-gas event, and thus providing the opportunity to include off-gas detection as an effective barrier to help prevent thermal runaway in lithium-ion battery systems. And the other thing that you'll note on there is that when the hazard has gone away, the off-gas signal does return back to normal. So in this case, you're also indicating that that gas that was generated during that momentary event, while it peaked, it also recovered, and at that point, that gas was cleared from the area. So that's a very brief overview. I think we're going to turn it over to Nick Warner now to talk about his, and then I'll be back on when we talk about questions and answers.
That's right, Steve. Thank you so much for that great overview on lithium-ion off-gassing and how using it can help prevent thermal runaway and fires. It's now my pleasure to introduce another CISA member. So we're joined by Nick Warner. Nick, if you want to share your camera, that'd be great. Nick is co-founder and managing principal of the Energy Safety Response Group. He's a co-founder. Oh, and prior to founding that company, Nick worked as an independent consultant through Warner Energy Storage Solutions and was a senior test engineer at DNV. Nick has also led efforts to develop the Alternative Energy Fire Research and Training Center in Piqua, Ohio. And before leaving DNVGL, Nick led the development of the industry's first third-party controls and battery management system validation testing services, as well as streamlining DNVGL's explosion modeling efforts and permitting efforts for ESS. Nick is heavily involved in standards activities, including UL standards and NFPA and ICC codes for fire safety and energy storage system deployment. And he's really passionate about energy storage safety. So Nick, we're so glad you're here, and please take it in with your presentation.
Great. Well, yeah, thanks for having me. I know we're tight for time, and everybody wants to get into the Q&A, so I'll move through this quickly. But if anybody has any questions about what I'm talking about, certainly happy to discuss. Yeah, so just a quick overview of ESRG. We are a relatively new company, about 1.5 years in operation now. And we also just recently rebranded from Energy Storage Response Group to Energy Safety Response Group to kind of better advertise the broader industry focus we have now. While we originally started out looking at all things safety related for energy storage, our expertise in a lot of the areas necessary to do that competently in energy storage has lent itself well to natural gas, to wind, and now hopefully soon to PV as we continue to grow. And so, you know, as Melanie mentioned, I'm involved heavily in codes and standards activities, and a lot of what I'm going to talk about here is going to relate to that. But in support of that mission and what we do with permitting, at the end of the day, ESRG really is a test organization. Consulting is certainly a big part of what we do, advising people, helping people build safer batteries, get those batteries installed and in the ground, keep them operating safely, and then ultimately helping them dispose of them safely. But that all starts with testing and design. So a lot of what I'm saying, a lot of our critiques with our clients and industry as a whole comes from what we see when we get a chance to poke and prod and overcharge, overheat, over discharge energy storage systems. When we couple that with our background in public safety as firefighters, as engineers, as public safety experts and failure investigators, it really gives us a unique perspective on what's going on with industry, where things are going, and hopefully, puts us in a position to help industry do things better, as well as help our customers do something better. So you can go to the next slide, maybe hold for a second or so, but kind of covered everything there. Again, we're engaged in UL 1973 testing, UL 2580 for electric vehicles, a lot of UL 9540A, but really our passion in a lot of ways is pre-certification testing, helping people build safer battery systems, and doing that through what we find in the destructive testing. So next slide, please. So ultimately, what I want to talk about, what is the industry doing today? What could they be doing better? What are the challenges we're seeing in terms of how we get systems permitted? What are people still misunderstanding? And then we'll talk too about how people can improve this. So what is the industry still struggling to digest in this current regulatory environment, especially one that's changing fast? What is 9540A? It's a question and a conversation I have multiple times a day. What do we need to do to satisfy the requirements? Who's responsible for running those tests? The manufacturer. Do I need to do it? Hey, I built a custom system. Do I really need to test it for a one-off application? What does this mean for my 9540? If I'm doing a field certification, a listing, in terms of the bigger regulatory picture, where is this actually getting me? And then I did the test, now what? How does this mean I comply with fire codes? California has a fire code based originally on the 2018 IFC. July 1st of this year, just as we're all starting to get comfortable with that, we're jumping to a new language based on the 2021 IFC, which is going to be not quite a radical departure, but a pretty substantial change from where we are now. It's going to mean a lot of things for the industry, and my guess is going to raise that hurdle up another notch yet again. So next slide, please. With all that said, the big struggle and what I want to talk about today is 9540A fire testing, how it's being conducted, what the results mean, how the results are being interpreted, and what does that mean for code enforcement. To be entirely honest, while legally all nurdles are equal in a lot of ways, the results coming out of these test labs are not consistent with each other. They're not consistent in a lot of cases with the spirit of the test. In some cases, they're not consistent with the letter of the test. As AHJs get better educated on the subject, and I know tomorrow there's a meeting of California fire protection officers where they're going to get another great talk on coming code changes, on how to interpret UL 9540A results. As folks learn this better and better, the ways in which the codes are being enforced are changing. There's not a lot of consistency jurisdiction to jurisdiction. Certainly when you go from East Coast to West Coast, things get another degree of complication. And all of this is kind of manifesting itself in a way that is resulting in continual delays to permitting, continual costs to permitting, liquidated damages in some cases, getting systems in the ground because of delays, because of additional requirements folks need to meet, and ultimately is slowing down deployment of energy storage, which is what ESRG was founded to help or to prevent, and to keep things moving smoothly, to get these systems in the ground in mass, but also safely. So next slide. So where we've kind of arrived at today is there are three kind of systems out there. There are systems that were installed before there were any type of code at all. A lot of those out there, but over the next year or so, we're going to see a lot of systems that are going to be installed that kind of sort of meet code compliance, that may have incomplete test results or inconsistent test results, and may have a lacking analysis of those results, that really just kind of slipped in under the radar, may not have had an AHJ who fully understood what they were looking at. But in general might make it today, but when you go to permit that same system a year down the road, or if something happens with that system, they may run into challenges with continued operation. To what Steve discussed earlier with respect to Li-ion Tamer, there's actually a proposal coming in NFP 855 for the next revision It's going to require retroactive installation of some type of gas detection or some other way to manage deflagration in systems that are already out there. At the end of the day, we know batteries are flammable. We know batteries emit gas. There's becoming increasing concern in the public safety community about the industry and about the public safety community's ability to manage events in these things in a safe manner, in a way that everybody gets to go home when it's over, in a way that makes the community feel safe. Given how quickly codes are changing and adopting, or being adopted, I suspect that we'll continue to be in a bit of a state of flux. But ultimately, when you get out ahead of this, when you go above and beyond what's in the code right now, you're taking a step to ensuring that you're future-proofing your system. So the good news is we're seeing a lot of implementation of safer designs coming down the pipe. We're seeing a lot of implementation of gas detection to detect this early, in some cases to prevent it, but in some cases just to inform the fire service about what the risks are. We're seeing a lot of safer passive designs too. And in some cases, this is actually making running the test a little more difficult. But at the end of the day, it's going to bode well for the industry. So if you want to jump to the next slide, and then ultimately the one after that. Thank you. So, what I want to suggest to everyone today, as we look at where the codes are heading, how to future-proof your system, the biggest issue is how to run this test, how to run UL 9540A. The public safety community is starting to understand this. They're skeptical when people come in with a test showing only a single cell failure. And actually, if you want to jump to the next slide. At the end of the day, we know these batteries are flammable. We know they're emitting a lot of gas, as Steve talked about, as Li-ion Tamer has done testing one, as a lot of others have done testing one. We know gas emission is coming. We know these things are flammable. At the end of the day, if you are running testing that doesn't accurately reflect that, so if you want to jump to the next slide, if you're running testing that doesn't reflect that, if you're running testing that doesn't seem to jive with some of the worst case scenarios that we're seeing, you're probably not running the test properly. My advice to most of our clients and to folks on this call is, when you're running your 9540A testing, don't be afraid to light the thing up. At the end of the day, 1973 is your demonstration of cell-to-cell safety protections. 9540A is intended to better understand what the worst case scenario is going to be. Don't stop putting safer designs into your system. Don't stop putting after detection in there. Don't stop putting means to detect this and shut it down. Excuse me. On that note, I'm out of time, so I'll wrap this up. Don't be afraid to light the battery up and really put time into the analysis. We're seeing more and more systems get rejected, both on the East Coast and on the West Coast, for inadequate testing results, for inadequate analysis of their system. When things are done, don't be afraid to go the distance. Not just look at what you saw in large scale testing, but look too at what the worst scenario you didn't get to was. Hey, you got a design that only allows for 2 or 3 cells to catch on fire before it ultimately is able to contain itself, to put itself out, whatever it is. That's great, but humor the AHJ. Don't be afraid to go a step further. These guys see dangerous, risky stuff all day, every day, and coming in with a battery, or a claim that a battery isn't going to burn, isn't going to go into thermal runaway, isn't going to do a lot of things, is going to be met with skepticism. And so jump into the last slide. Kind of tying this all up and leading in for Tom, future proofing doesn't begin and end with testing. Certainly running the test better, keeping up with the proper versioning of the test, with the proper versioning of requirements in NFPA 855 and the International Fire Code, California Code is all great, but continue to go above and beyond. It's going to pay off in terms of smoother permitting. It's going to pay off in terms of reduced liability. It's going to pay off in terms of increased comfort with your system from public safety, from code officials, from anyone reviewing it. That means emergency response planning. It means knowing the role of subject matter experts. It means being able to provide the data from Li-ion Tamer, the data from gas detection, the data from IR, whatever it might be, in a way that's meaningful to everybody, and getting that information to the people whose lives may be at risk by responding to these systems. If this needs to be supplemented by a third party, certainly it can, but that needs to be incorporated too early on in the process to make sure that it can be done properly and, again, integrated safely and smoothly for everybody. So with that, I'll turn it over to Tom and let him talk about how Duke has done that.
Great, thanks so much, Nick. Really interesting. We're getting some great questions typed in to the webinar, a lot of them around battery chemistry, so I'm sure we'll get back to that at the end of our Q&A. But for now, I'm pleased to turn this over to Tom Fenimore. Tom is Business Development Manager at Duke Energy and a professional engineer. He has 30 years with Duke Energy in customer-facing and regulated BD roles, and he's currently the technical lead for the design and implementation of fire safety systems for regulated energy storage and microgrid projects. He works with internal and external stakeholders, engineering groups, and vendors to accelerate the deployment of renewable technologies, including long duration energy storage. And Tom, I find you quite amusing and funny and charming as well. So we look forward to your presentation. Thanks so much for being here.
Thank you very much, Melanie. And it's a pleasure to be with you today and have an opportunity to share a little bit about what we're doing at Duke Energy. As Nick has pointed out and Steve before me, lithium-ion energy storage safety, is a large and a rapidly changing topic that is out there today because of the influence of technology and the knowledge base that we've got around it. If we can go to the next slide. So at Duke Energy, our typical projects to date have consisted of lithium-ion NMC projects. They're typically containerized systems, very much like a lot of folks across the industry have been deploying. They're custom-built 50-foot container type projects, in the industry kind of known as the shipping container, but they are custom concrete containers with redundant AC on them, outward-facing doors, no internal access or walkways. They basically resemble a data center for the most part with a hot and cold aisle type arrangement. Our containers have 7 layers of safety systems deployed in them. We'll cover them a little bit of detail going forward. But our typical building block approach that we've taken is kind of this 2.5 megawatt hour capacity container using the Samsung SDI modules to date. We've got 52 racks, 13 modules in a rack, 676 lithium-ion battery modules in a container at 22 cells per module for a total of 14,872 lithium-ion battery cells in a container. So a typical site would have 2 to 4 or more containers. So lots of opportunities for things to go wrong. I don't mean to be negative about it, but I'm the fire safety guy that they point to at Duke Energy and say, do you have me covered? So these are the kinds of things that keep me up at night. On a 5 megawatt site, I've got 30,000 opportunities for that container to cause problems for Duke Energy. Next slide, please. So how are we engaged? Well, we've taken a corporate approach. Although I've got the lead for our regulated side, we've engaged very heavily with organizations within and outside of Duke Energy. The first folks that we reached out to were our folks in the generation side of the business, to learn from them what their best practices are. Our environmental health and safety folks internally, they're not shown on this, but we've got a very good working relationship with our folks on the generation and also our environmental health and safety folks within Duke Energy. And, we are partners in this. They want to see it succeed. Our, path forward in terms of getting to carbon neutral is going to require us to have a lot of energy storage on the grid. So from that standpoint, we do a lot of our own technology testing. If you look at the top of the screen there, you'll see a little snapshot of our Mount Holly Emerging Technology Office Lab. We were able to do some testing there that I'll talk about. But we also stay very heavily involved with industry organizations, NFPA, IEEE. We've got consultants on basically retainer for the most part, American Fire Technologies. We've got weekly updates, with our consultants at American Fire Technologies who do a lot of work for Duke Energy across our fleet of generation, and now also on our energy storage side to stay abreast of what's going on in the industry. We're also heavily involved with the Energy Storage Association and also EEI. Basically all of the things that touch energy storage, we want to know about and we want to stay involved with them. Next slide, please. So we had an opportunity back in 2018 to work with Nexeris Li-ion Tamer to actually test out the Li-ion Tamer technology. It was relatively new to the stationary energy storage market at that time. And Steve and his partners at Nexeris reached out to us and said, hey, do you guys have a battery, that we could get access to where we could do some testing? So we do have a site. It's at our Mount Holly site that I referred to in the previous slide. We have a 650 kW SAF battery that is used for research and development purposes for microgrid testing. And in that case, we were able to get access to it and actually install a prototype of the Li-ion Tamer technology. And, I'll tell you about that initial installation was really difficult because the wiring techniques at that time were really challenging. But, that's why you install prototypes. That's why you test. You go to the field, and that's why our Mount Holly site was created, to understand what we were up against in deploying these new technologies. So we installed that initial prototype test in Q3 of 2018. It was functional, but those 6 sensors that were installed on those 6 racks of batteries, and actually another sensor for the HVAC, took us about a day and a half to install. And we, came back to Li-ion Tamer and said, that's kind of a non-starter. If you take a look at a typical container with 50 racks or so, you're going to look at a week's worth of installation for that thing. We can't live with that. So I'm pleased to say that Li-ion Tamer turned it around, came back with a production unit. And if you go to the next slide, in the first quarter of 2019, they actually changed their wiring techniques over to Ethernet, RJ45 cabling. Basically click on the sensor end and click on the controller end. And the installation of the new Li-ion Tamer technology at that time went extremely fast, using standardized cabling that you can get at any supply store for Ethernet. And we were able to take the existing prototype system out, install a production system in its place. And that production system is actually tied into our microgrid controller, sending signals back and forth should we have a problem with that system. So since then, we have standardized on the Li-ion Tamer product as our early detection system that gets deployed on every energy storage project that we do at Duke Energy. Next, please. So what else do we do besides Li-ion Tamer for energy storage safety? Well, we've got basically a 3 section approach to it, but we've got 7 different systems plus the site systems that we deploy. Obviously, we're relying on the battery management system as our first line of defense. We work with the manufacturers and make sure that their battery management system meets the specs that we need. We're not afraid to do testing. We've actually taken manufacturers who want to get on our approved vendor list and have them submit a rack with modules and a battery management system to the Battery Innovation Center in Indiana, and actually do testing of not only the battery performance, but also the battery management system testing, or battery management system safety systems. Beyond that, after the BMS, our next line of defense is the Li-ion Tamer system for off-gas detection. And that helps us protect at the cell, module, and rack level with those 2 systems. Then we move on to a container ventilation system. All of our containers can have an exhaust system that allows us to be able to bring fresh air into the system and exhaust any gas buildup that we might have inside the container. That is automated. It's controlled by the hydrogen and CO sensing systems when that needs to take effect, or we can manually control it from the emergency response station that I'll address in a minute. Going beyond that, we have the classic fire alarm control panel with smoke and fire detection, hydrogen and CO sensing providing inputs to that. If that system activates, it will release the clean agent fire suppressant, typically Novak or FM200 type clean agents that are deployed inside the container. Hopefully at that point, we've got the system under control, but should we not, and we get into a system, situation to where we have to, deploy water to it, we've got a sprinkler or a deluge dry pipe system piped into all of our containers that are on these sites. So a line is run out to the emergency response station, and a tanker can be hooked up from the fire department, and we literally can flood these containers should we need to. And then last but not least, if we did have a system get into complete runaway and we had a buildup of hydrogen gases in the container that somehow were not exhausted, we require a full-blown explosion analysis, no pun intended there, but we require a full explosion analysis to be done on the front side of the project so that we maintain a 1 PSI or less pressure wave at the fence line at the site. So we want to ensure that should we have an explosion, that that pressure is relieved in such a way that we don't injure any public or damage any property outside of the fence line at the site. And then last but not least, we don't want any personnel to enter a site without Duke Energy's approval. So we have an emergency response station that is placed at the front of the site to keep our first responders safe and allow them to have the information that they need at a panel that gives them the fire safety information. It gives them, the off-gas event information, as well as control of the exhaust systems and also access to the deluge systems as well. And that is a standard on every site. Next slide, please. And then beyond that, as Nick mentioned earlier, we are finding out that first responders training is absolutely huge. We have sites that are managed and basically cared for by not licensed, but paid first responders that are, on a city's payroll. We have other ones that are, on Army and Navy bases. We have other sites that are in rural areas, all by different first responders. And we're finding out that first responder education really needs to happen early in the project and needs to be followed up on continuously. We're pleased that we've got on our staff a former firefighter who is deeply engaged in this effort and working with our environmental health and safety folks. We're producing literature, we're producing training aids, and we're really staying on top of it to continually engage our first responders to make sure that they stay safe and they know the right way to engage these sites should we have a catastrophic event. Next slide, please. I think that's it. No, one more. So, what do we put out there when we go out to the street for an RFP? Well, we have a full set of fire safety design criteria that's included that goes to the vendor. That design criteria is in version 4 now because it's being revised to address these smaller containers that are coming into the market. Fluence and Wärtsilä and CATL are bringing different container configurations than the large shipping containers. We're building 2 sites with those types of containers, and we're going to take those projects and actually from those designs address our new fire safety design criteria. And one of the things that we're learning is that the different system architectures require some different approaches, but they all need to be NFPA and UL compliant wherever we can. And one of the things that we're learning is that we need to remove the vendor interpreting our specs and we need to get more specific in telling them exactly what we want on the front side of our RFPs. Next. That's it. I appreciate the time and look forward to your questions. Thank you.
Great, thank you so much, Tom. Really appreciate it. And now I'd like to invite all of the speakers to turn their cameras on and we can kind of kick off this discussion. So I'm going to start with a question really about why Duke would apply these high safety standards and where the mandate for having these high standards is coming from in your organization. We have a lot of utilities on the line. This is about how to design battery storage safety for your RFQ. So yeah, we'd love to learn about that. And then Steve, also maybe your comments on some of the pitfalls or I guess the outcome of safety results that have on the brand of the utility as well, and who owns the disaster when it happens. So Tom, I'll kick it to you.
Yeah, so, great question. And so, as I said, we are heavily involved in working with our environmental health and safety folks. And our environmental health and safety organizations do risk assessments of all of our assets in terms of fire safety and, personnel safety and up and down the line. And we went through just recently, about 3 months ago, a full-blown assessment, a risk assessment of all of our sites to determine, what the potential risk is to the corporation, the potential risk is to the asset, and the potential risk is to the personnel that are involved with these projects. And, we had to prove basically to our internal environmental health and safety group that we basically scored, green, meaning that we were able to continue building sites and did not have to go back and revise those sites. So with additional safety measures. So, I guess from that standpoint, from a, safety systems cost perspective, we're our own worst enemy, because we're kind of throwing the kitchen sink at it. Everything that's available in the market from a safety perspective, we want on board our projects. But quite honestly, the brand of Duke Energy, being one of the largest utilities in the country, simply cannot, stand a major event of any type out there. And we want to make sure that the brand gets protected. But beyond that, we want to make sure that the public gets protected, and that any first responders are protected more so than anything else. So, I go to bed each night knowing that from that standpoint, we're doing everything we can from a systems perspective to make sure that we're keeping things safe.
Thanks, Tom.
Cool, yeah, thanks. I guess, Melanie, I'll touch on that just a little bit as well. And Tom kind of talked about it from the utility perspective in terms of protecting brand. But that's, one of the things that we talk about at Li-ion Tamer a lot. And that's why we focus on barriers that can be added in that preventative region, whether you're looking at the, the stages of the battery failure wheel, or you're looking at that hazard mitigation analysis and looking at those threats. And how do we keep those threats that might start off small, but how do we keep those from escalating into something that will result in one of those top level events, and then you have to deal with the consequences of that failure. And so that's, that's really one of the areas that we focus on quite a bit. And another thing that, we've begun to really focus on more and more is focusing on the insurance side of this. That's one of those discussions that's always been kind of 2 steps ahead of us. But we're, beginning to work more closely with insurers, understanding what concerns they have. How do we manage risk from an insurance perspective? And that's another big aspect of one of the things that's on the horizon for what we're doing.
Thanks. So this question is for Nick and Steve. Some curiosity around different battery chemistries. So basically, is there a chemistry that might be more predictable in its off-gassing? Maybe it off-gasses sooner, or preferred cells that will lead to, safer results or a slower thermal runaway process?
Steve, you want to go first, or do you want me to take that one?
Go ahead first, and I'll fill in the back end if you.
So from ESRG's perspective, when we're putting together ERPs for the fire service, when we're talking to the fire service about the different chemistries, we do not make a distinction. While we would be remiss to not acknowledge that in general, iron phosphate tends to take a little more of some types of abuse before failure, is a little less prone to self-ignition during failure. At the end of the day, if you have an event with one of these battery systems, whether it's a metal oxide cathode material or whether it's an iron phosphate, it doesn't change how the fire service is going to respond. It doesn't change what the ultimate risks are or really make a difference. While we found that LFP obviously is more thermally resilient, there are other failure modes that it actually doesn't do quite as well as, say, an NMC. So being a big fan of analogies and trying to convey this to the fire service, what we're kind of telling folks now is it's kind of like diesel fuel and gasoline. One might be a little harder to light on fire than the other, but at the end of the day, if you've got a puddle of each and it's on fire, it doesn't really matter to your response. So I'm sure Steve has more to share in terms of what they've seen at the gas level, but that's our position.
Yeah, and Nick, that's I think a fair analogy on it. And we do, similar to your response, we acknowledge that there are some that are more thermally stable. An LFP battery, for example, if you're doing a thermal abuse, you do have to get to a higher temperature to put it into that state of thermal runaway where those mechanisms are becoming exothermic and occurring inside the cell. From a gas detection perspective, while the cocktail can vary slightly, we still see very, very similar trends in how you progress from the initial venting of a cell that it is primarily the solvents that are used in the electrolytes before you get that temperature high enough to start a lot of the decomposition that occurs at thermal runaway. And then as you progress into thermal runaway, that cocktail of the gas release changes into more of the hydrogens and COs. And that is really independent of what the chemistry of the battery, of the particular battery is. So we see a lot of, from a detection point of view, we see very similar behaviors, even though we can have different behaviors from kind of the thermal stability side.
Great, thank you. So we also got some questions about, I would say, retroactivity or once a battery is already designed. So it sounds like a lot of the testing that Tom did was on the commissioning side for a new battery system. What happens if, say, you're implementing a second use application for, say, an EV battery? Or if you've already installed an energy storage system, it doesn't have off-gas detection, what can we do with batteries once they're already installed in order to ensure that they're safe or meet the changing codes and standards?
Sure. No, Tom, Steve, I'll start with this if you guys are okay with that. Right out of the gate, at ESRG, we look at safety holistically. Like I mentioned, there are a lot of different types of batteries out there. Some of them, the battery itself may be problematic. Some of them, maybe the design of the module is problematic, the design of the rack, the BMS. At the end of the day, nothing is perfect. And while systems are getting better and better every day, not everybody is great at everything. Looking at chemistry, what we've actually found is form factor in a lot of cases can be a bigger driver of overall cell safety and stability than the chemistry itself. So when we look at safety holistically, if you don't have a great battery, if you don't have a great module or a great rack, you can still do things at a higher level, even if it just comes down to like what Tom talked about with training. As long as the fire service is aware of the risk, you can still reach an acceptable level of safety for that system. There's a lot of ways to do that. In terms of retroactivity for a system, what a lot of people don't understand now is that if a code official determines a system, any technology, not just batteries, to be a risk to public safety, they can come in and retroactively require you to do a whole manner of things. It's not just a matter of whether or not the code says they can do it. If you read 855, there's clearly stated language in, I believe, chapter 1 of that document that states when a fire code official can or cannot come in and apply retroactive changes. It's not common that a code explicitly calls for retroactive changes to systems that are already installed, but we may have, we may be at that point with 855 soon. And so from an industry perspective, at the end of the day, you need to do what it takes to make your system safe. I didn't get to address this point in my presentation to get through it, but at the end of the day, if you're being lazy with testing, if you're not doing the right thing with safety, even if your system is already in the ground, if your name is on it, if you're owning it, if you're operating it, you're responsible for it. And whether or not you make the fire marshal come in and be the one to be the bad guy and make that system safe, there are a lot of ways to do it, and it's not just the right thing to do. In some cases, you're legally required to do it.
Yeah, and Nick kind of alluded to this during his presentation, but the APS report from UL actually gives recommendation for retroactivity on the explosion control aspect of the fire code. They identified that was one area that, that they did make recommendations for retroactivity on. And we've seen that honestly quite a bit from our side of the business. I think there's a lot of learning that continues to happen from both the failures that occur within the industry as well as just the testing and general progression of knowledge in the industry. And we have done quite a bit of retrofits and continue to do that today, and can go in and install, like Tom said, these things go in very quickly now. And as long as we can just tie it to an e-stop, we can meet what FM Global is now recommending in their 533 property loss prevention data sheet is to shut down the battery system at the first sign of that gas, because that's the point in time when these things become abnormal. Don't mess around with it, get it shut down and understand what's going on.
Great. Well, thank you so much. We're actually a minute away from the top of the hour. So I want to thank you, all three of you, for your expertise and for being here today. We've gotten recommendations that Duke publish a safety manual. They need help in Europe. New York needs help. California needs help. So certainly there, people want to learn from you. And everyone who submitted questions, I will be disseminating them to the speakers. So hopefully they can follow up with you. And again, this webinar was brought to you by the California Energy Storage Alliance. And we look forward to continuing the safety conversation with these great speakers. And I'll just turn it to Steve if you have a brief closing thought.
Well, thank you. We want to just thank CISA for the opportunity to have this conversation about safety and your support for safety within the industry.
Great. Well, thank you so much, everyone. Have a great afternoon.
Thank you.
Bye-bye.
Take care now. Bye-bye.